So what I'm going to do today is work through several examples, okay, of numerical examples where we do it in MATLAB, Simulink, but you should also be able to do the same thing by hand to some extent. This is a problem that I'm going to face when I want to test you on this in the second midterm. What is your feeling, second midterm? You guys feel comfortable to have it in the computer lab? Yeah. You have to plunge, you know, otherwise you're not going to plunge yourself into. Well, maybe we can do one thing. Like I can have a quiz there to force you into this environment. Meaning a quiz would be worth less in terms of maybe the weight of an assignment, but you get to do it in a constrained environment. An assignment you get exposure to MATLAB and Simulink, and I will have more of those coming up in the future assignments. But can you do the same thing in, I don't know, it's even important to test that, but you are being exposed to that, and I guess it is important for me to know that you are comfortable with it. Actually, the answer is no, but I don't know whether it is actually possible to enforce that here. Right. I know. Typically, the way that I run a test on the lab would be to ask the IT guys to come and prepare the lab for an exam. And that means a certain set of things that they will do for me. First, cut off the internet access.
Have you tried that? Have you actually tried that?
In other places, not here.
So try.
Why? It doesn't work? No. Have you had it in any other course? No. You have not had it in any other course? Right. So the system should be able to support that. I'm not even sure whether they can support that kind of a testing environment. They'll cut off email, they'll cut off internet access, and then they will cut off all the access to external drives. And they will create two drives. One drive in which I distribute material to you for the exam. And there I could put in programs that I think you can use it, take it, and change it. And I have not talked to Ron yet. You are discouraging me already. All right. This is the first time I'm teaching here, first year, and control for the first time. So I need to figure out what is possible and what is not possible. No, I'm not. I'm actually substituting for Dr. Ramagnoli. He is the one who teaches Compress course. But since they offered it the second time and he was a bit tired, I offered to do it. And me? Yeah. Oh, I'm lucky. I don't know. Because from what I've talked to him and what I understand is that I'm pushing you more in MATLAB and Simulink than what he did. That's good to hear. All right. So I'm going to do 4 examples today, building on the problem. We looked at building the block, and that's an important integrative step that we need to take. We know how to analyze the dynamics and how to do it in Laplace domain in terms of transfer functions, but putting the whole system together in terms of the feedback system also. And this is the feedback loop that we constructed for controlling the outlet temperature T prime in terms of the deviation variable of the tank. So this is what we want to control, and this is the process. And this is the measurement, and this is the control. And so it has all the elements of a typical control system. Okay? The process could be much more complicated, the control action could be much more sophisticated, and this is a disturbance. And that is the set point. And all these features are built into the control station software that you have. But for a few specific processes, like a two-tank drainage or a heat exchanger or a distillation column. Whereas what you are learning is to be able to plug any process model in this place. Instead of that block, you can put in any, if you have a model for a fluidized bed reactor that you want to control, you just have to know the transfer function for that and put in there, and you have a control system. And there are several parts to it. One is controlling it for disturbance rejection. The other one is controlling it for servo tracking of a set point. And the third aspect would be designing a controller, which means tuning the control parameters and look at the response and see which response is more desirable and what should be the tuning constant. These are knobs typically in a control station, a control process. So this is the specific process that we're talking about. So in this example, we are told that we have a tank with 1,000-liter capacity. Okay? So the volume of the liquid is 1,000 liters, and it is getting water at a rate of 200 liters per minute. And the exit rate is also the same thing, 200 liters per minute. So there is no change in the flow rate. The flow rate is constant. But the inlet temperature could be changed. It is coming in at 60 degrees and leaving at 80 degrees under steady-state condition. Okay? So the first question that you might be asked is, find out what is the heat input? How much of heat should I put in to increase the temperature from 60 degrees to 80 degrees? And that's a fairly straightforward first course in chemical engineering that you do, heat balance, and you can find out what the steady state is. Okay? And the remaining four problems that are posed are the following. Determine the response of the outlet temperature to a step change in the inlet temperature from 60 degrees to 70 degrees. The inlet temperature changes from 60 to 70. What happens to the outlet temperature? What do you think intuitively for this problem? Without looking at the solution. Constant Q. It will go up by how much? 10 degrees, by the same amount. Okay? Because the heat capacity is constant, the flow rate is constant, and if the heat rate that is input is also constant, it should increase by 10 degrees. The next question one may ask is, okay, how long does it take to reach that 10 degrees? That is a difficult question to answer. You need to look at the dynamics for that. And the next part is determine the response to the outlet temperature of the tank to a step change in heat input. This time it is at 60 degrees still, but the heat is increased to 42 kilowatts, by 42 kilowatts. So whatever the previous value was, you increase it, because we are all talking in terms of deviation variable. A step change in heat input of 42 kilowatts. The third one is a combined one. Okay? So in the first one, you only increase the temperature. The second one, temperature is the same, you only increase the Q. The third one, you increase the temperature by 3 degrees step change and increase the heat by 42 kilowatts at the same time. So what would happen to the outlet temperature and what is the dynamics, how long it takes, etc. And plot the response, basically. And the last case is the temperature is increased by 3 degrees from 60 to 63, the inlet temperature, but the heat is decreased by 42 kilowatts. Okay? What will be the outlet temperature response? And you can do this in MATLAB, and we will see how to do it in MATLAB. You can also build Simulink models for that. Okay? So any questions on the problem? These are the kinds of problems you should be able to do by hand in an exam here. Okay? And I will keep the problem simple enough that you will have at most a second order system. Okay? When you're doing the inversion partial fraction, you should be able to do that. Or I will take you through that step. If it is a more complicated one, this is the partial fraction expression, and then construct the dynamic response. Okay, what do? We know from the previous analysis that it's a control problem. If laid out 4 questions we need to answer. Is there a control element in there? There's really no control element. The control part is not there. All it is what is the outlet temperature response when I change either the inlet temperature or the heat input. So we're looking at only this part, okay, this part of the loop. If I change Ti prime or if I change Q, how is the outlet affected? Okay? So all the questions are centered around that part of the loop. The next problem, we will analyze specifically the measurement. And in the third problem, we'll put them all together as a control. So the whole control problem is a feedback control where the information feeds back and affects the process temperature. Okay? So the first problem is only about the heater itself. That's the first thing that you need to understand. You need to understand that because you need to pull out the corresponding transfer function for that block, which we derived in the previous lecture, which says that the outlet deviation variable is related to the inlet heat rate and the inlet temperature. Okay? So this transfer function either you may have to develop in an exam or it is given and you need to analyze. Okay? So in this case, we'll take it as it's given and you need to analyze that, meaning you need to find the constants that are appearing in this transfer function from the problem description. So the first thing that you need to find out is what is tau? What is the time constant that appears in several places? Okay? The time constant is given by rho V divided by W. Okay? Basically, it is the tank volume divided by the volumetric flow rate. What question? Yeah.
How did you know that right off the bat?
What? The time constant is given by rho V. No, it appears in the model equation. So let me just pull that equation from the previous lecture. It is also the residence time. Okay, I just want to show you the differential equation that you would use to figure out what the time constant is. There you have, okay? So rho VC divided by WC, okay? Divided by WC. So the C and C cancels out, rho V over W, that is the factor that typically multiplies the derivative term. And that is what tau is, okay? But as we pointed out, it is physical interpretation of that is, it is the residence time. So tank volume divided by the volumetric flow rate. That tells you approximately in 5 minutes, you would have added 1,000 liters. So the original 1,000 liters in the tank would have been displaced. Okay? So whatever the new temperature that came in with, typically of the order of the residence time, it should be the outlet temperature too. Only exactly one time constant, typically 3 or 4 time constants it will take for. So without actually solving it at this stage, if you find this number 5 minutes, you can tell that it will probably reach a new steady state. Whatever the step change that I put in, 5 degrees, 10 degrees, 20 degrees, whatever it is, it will reach a new steady state in the order of about 4 times 5 minutes. Okay. So about 4 times the time constant. And that is one number that we need. The second number that we need in the transfer function is the 1 over WC. Okay. Tau we already obtained, and we need to obtain 1 over WC. And here you need to be very careful about the units, because a common mistake that people make is, we already talked about when you have a block diagram, what are each input and output stream will have a unit associated with it. And the transfer function should have a consistent unit, so that when you take transfer function multiplied by the input, you get the correct output. So pay particular attention to what this units of this number 1 over WC are. 1 over WC appears in here. It is 1 divided by WC times QF. Okay? So that's why I'm just writing it as 1 over WC. So it is, the flow rate is given as 200 liters per minute. Okay? So the C, the specific heat is 4.184 kilojoules per kg degree C. That is a property, material property, the heat capacity. Okay? So I need to convert the liters to kilograms. Okay? So I take the density and multiply it by 1 kg per liter. Okay? So what has happened here is I've canceled the liters with liters. So I'm getting so many kilograms, 200 kilograms per minute is the mass flow rate. W is the mass flow rate, so it is so many kilograms per minute. And then I have this kilograms appearing here that cancels with kilograms. Okay? And I have minutes, and I want to convert that into seconds for the reason of just joules per second is watts. So I multiply this by 1 over 60 minutes per second, canceling minutes to minutes, and then I have the number in seconds. So the net effect of 200 times 4.184 divided by 60 is 14. Okay? And the units that are left with are kilojoules per second per degree C. Okay? So the units are degree C in the numerator divided by kilojoules per second or kilowatts. Okay? So that is 1 over WC, and so it's going to convert kilowatts into degree C. Okay? So if I take and draw the block diagram for only that part, that is Q. Input is Q, and the output is T prime, for example. Ti is 0. Okay, there is no change in the inlet temperature. I have only the change in Q. So Q should have the units of kilowatts. That stream, Q, will have the units of kilowatts, and the outlet stream should have the units of degree C. So this transfer function that I put in here, 1 over WC, must have a consistent set of units. Okay? So that when I multiply it by kilowatts, it gives me degree C. And that is what is happening here. It is degree C divided by kilowatts. So Q times this 1 over WC will give me the units of a temperature. Okay? So the input Q multiplied by the transfer function. In this case, the transfer function is just a number, 1 over WC. Any questions on that? And Simulink will not know the units. Okay, so you need to figure out the units and put the correct numbers. For Simulink, it is just some number coming in, some transfer function operation, it just multiplies it and produces the output. Okay, so if you have an error in units, that error is going to be carried through. Okay, so we saw in the last class again that we can write this expression for the transfer function in one of two ways. By factoring the common factor, for example, 1 over 5s plus 1 is a common factor. And when you have that, the Simulink block diagram is going to look like this. So Q is multiplied by 1 over WC with the appropriate units, and then it is added to Ti prime. Okay? 1 over 14 times QS plus Ti prime S. So this is what is in the entire square bracket, and that, after adding, it goes to 1 over 5s plus 1 to produce the T prime. So it's not a control problem. This is called the open loop system. Okay, so you just have an you've opened up the loop, there's no feedback, and whatever you input is going to affect the output. Manual control in one time would have been just this. When you don't have a feedback control system, what does the operator have to do? The operator has to figure out, and this problem you'll see as you go through the 4 sections, you will see what is happening, how does the manual control work. The manual control would be, if the Ti, for example, increases by 5 degrees, I need to figure out how to compensate Q. So if the temperature increases by 3 degrees, maybe I have to decrease the heat input by 42 kilowatts so that the outlet temperature doesn't change at all. Okay? So for each change in Ti prime, I can figure out the corresponding Q prime. And as a manual operator, I just have to open the same valve or close the same valve to compensate it. Okay? And that is the process that we are automating now. Okay, any questions? Okay, so now we have the first question, as I said, is not thought of the 4 questions, is just to figure out what is the heat duty under steady state. Okay? So this is the steady state heat balance equation, and T0 is just some reference temperature. You'll find this cancels out, and Qs is equal to WC times Ts minus TIS. And the steady state, the outlet temperature minus the inlet temperature, multiplied by WC is Qs. And you know all of them. You know W, you know C, you know that inlet temperature is 60 and the outlet temperature is 80 degrees. So in order to heat that volume of liquid from 60 to 80 degrees, you need to input continuously 280 kilowatts from the heater. So that is your steady state heat duty. Steady state heat duty. Okay? Now the first question is, what is the step response to Ti prime when I have an increase of 10 degrees from 60 to 70 degrees. Okay? And so what is this? And there is no change in Q prime. Okay? So go back to this transfer function that you have here. So this block is not effective for part A. This block is not effective. So changing only Ti prime. Okay? So for part A, it is only Ti prime. And this transfer function 1 over 5s plus 1, that produces T prime. Deviation variables, all are deviation variables. So in this case, you are told that the step change is 10 degrees. It goes from 60 to 70 degrees. So the step change is 10 degrees. So you have figured out what Ti prime is. Ti prime is 10 over s. Because it is a step change, the transfer function is 1 over s. Okay? And that's it. So this you should be able to do by hand in an exam. Okay? And then now you need to be able to invert that, get the response in the time domain. There are many ways of doing it, Simulink, MATLAB, or by hand. Okay? So let me open up the MATLAB session. Okay? I probably need to switch between these two windows. So I'm going to define sims G and F. Not sure why this warning message comes. Okay. Now I'm going to define that particular transfer function. Okay, T prime S that you see, 10 divided by F divided by 5s plus 1. So G is equal to 10 divided by F divided by S divided by 5s plus 1. Oops. Okay. So that is the net transfer function including the step response. Okay. So if I want to get the result in the time domain, all I have to do is I Laplace G. Okay. So 10 minus 10 divided by t divided by e to the power t over 5. Okay. And that is what I've written down here. 10 times 1 minus e to the power minus t over 5. Okay, that's the response. Now we need to plot this, or if there are specific questions like how long does it take to reach from 60 to 68 degrees, or 80 to 88 degrees, how long will it take? So you should be able to use this result because this is a step response. Okay, any questions on that? You can do this in MATLAB in a number of ways. This is to get an analytical expression. But if you want to plot the graph directly, what would you do? You have to define S equals transfer function. This is one way of doing it, or provide the numerator and denominator. So G you define as 10 divided by 5 times S plus 1. That's another way of doing it, yes. So do I have the results saved? Yeah, it's still there. So you can say easy plot. And that. Yeah, I've already forgotten, but you have remembered. That's good. So there it is. Okay. But it gives you from minus 6 to 6. So you know already how to overcome that. Okay. So there are many ways of producing the plot. Okay. But the most common one that would be useful would be the step function itself, because it's part of the control system toolbox. Okay. So.
But you've already set.
Pardon me?
You've already set the
That's why I redefined it. I redefined G as 10 divided by 5s plus 1. So you can just say step G. The nice thing is step automatically plots only from 0 to the output. What's happening here? Okay. Okay. So you see that it goes from 0 to 10 in terms of deviation variable. As we expected, the outlet temperature should go up by 10 degrees, and that is what is happening. Am I going fast, or am I boring you? If you know all these things, maybe we should speed up. Okay. Is it fine? Okay. All right. So that is the step response for a 10-degree change in the inlet temperature. So let's go back to the notes, and this is basically a graph of this particular analytical expression. Okay. Now, here I have two graphs side by side. And what is the difference? On the left-hand side, you see plot in terms of deviation derivatives from 0 to 10. It's T prime. The right-hand side is actual sheet from 80 to 90 degrees. The outlet temperature for the original steady state, when we were putting 265 kilowatts or whatever, under steady state condition was at 80, it goes to 90 degrees by this increase in the inlet temperature. The heating rate is the same. Okay? So analytically, question? That's all you need to do. Oh, right. So analytically, all you need to do is to generate the graph on the right hand side. This is the expression that we have on the temp change from a deviation variable. So remember, the definition for the deviation variable, that's exactly what I am using. T prime is defined as T minus Ts, the steady state. That's the definition. All the variables are subtracted from the steady state. That's what we define as a deviation variable. So if that is the case, what should T be? T should be equal to T prime plus Ts, the steady state plus the deviation expression. So the steady state value was 80, and the deviation expression as you put. Now we can plot that again, easy plot or plot or whatever. Okay, so that will give you from in real numbers what is the change in the temperature. Any questions on that? There is no stupid question. It is not. Yeah, it is not convenient to do the transfer function because the transfer function in terms of deviation variable is valid at any steady state, right? Otherwise, you will have to carry the steady state part as a constant term throughout. Okay, and that will change. Whereas in here, the graph on the left-hand side is a universal graph. For any first-order system, that is the response. Okay. Now, instead of putting 265 kilowatts, if I put 330 kilowatts, the outlet temperature may be 90 degrees, but I can still predict 90 to 100 degrees how it will happen, simply adding that. Okay, so it's always convenient and advisable to work with the deviation variable, but you can work in the real variable too if you want. You'll be carrying an annoying TS term all the time. Okay, any other questions? So the second question was, when the heat input is stepped up by 42 kilowatts, okay, what is the dynamic response? This time, the inlet temperature remains at 60 degrees, but I'm just increasing the heat input. How does the outlet temperature change? So I could go back to my original transfer function that I had for both the variations and cancel the Ti prime term. Okay, so I start off once again with this transfer function that you see here. But this time, there is no variation in Ti prime, and I'm changing only Q. Okay? So the transfer function is Ts prime equals 1 over 14 times 1 over 5s plus 1 times Q. That is the part I'm going to focus on. That equation is the equation that we started off with. This is a, do I have a number? Not very consistent in numbering that. That is the transfer function for the block that I identified. So this whole problem is about this big block here. You see in red. Okay. So put that in Q or T prime, what is it? And we have written down as the 2 parts. First, we put that in only T prime. Now I put that in only Q. Next, in the part 3, we're going to put both of them in the same way. Part 4, we're going to put them in the opposite way, to get an idea of the control action. Okay, so let me go back. Part A. Part B. Okay, so the that input is a step change in Q by a magnitude of 42 kilowatts. So the transfer function for Q is 42 divided by S in terms of deviation variable. 42 is the addition from the steady state value. Okay? So that becomes your transfer function for the input. The transfer function for the process itself is 1 over 14 times 1 over 5s plus 1. That is the transfer function for the process. Okay? This is the process, and this is the input.
So far, we've only done step changes with one variable.
Well, in the next part, we will do both variables. When you say both variables, both C prime and Q.
Yes.
Right. Because of the superposition, it is additive. So that's the beauty about the linearization. Okay, so here I'm canceling this 42 with 13, so I get a net effect of 3. So the transfer function becomes 3 divided by S times 5S plus 1. Okay, so that's what I have here. G is 3 divided by 5S plus 1 divided by S. So this G is the total transfer function, input times the process transfer function. So that is the output transfer function. And that is, I don't think I need to go to MATLAB to type this in, right? You can see the same thing. Okay, so I Laplace inverts it and gives you the result as 3 times 1 minus e to the power minus q over 5. And you can see the pattern. Whatever the magnitude of the step change, that coefficient appears here. Whatever the time constant that appears here, that's why for a first order process, the response is kind of universal. And if you plot it as t over tau versus t prime over the amplitude, you get a universal curve, which you used in your first assignment, okay, first exam. So this is the net temperature response. 8e plus 3 times 1 minus e to the power minus t over 5. I don't have a graph for that. Maybe we can generate that. Okay. What would be one way of generating? G is equal to 3 divided by 5 times S plus 1. Okay, and then step G. So what do you notice here? The step change is going to result in a magnitude of change of 3. Because there's no Ti doesn't change, but that amount of heat, this is important to notice. I'm going to ask you a question later on. If I put 42 kilowatts step input, the temperature increases by 3. Okay. Now in the next part, I'm going to do both of them simultaneously. That is, part C is I'm putting in 42 kilowatts and I'm increasing the temperature by 3. What do you think the output temperature will be? By how much will it increase? That's it. You get the point now, right? So it is additive. Its superposition tells you that if you add 42 kilowatts, it increases by 3 degrees. But if you also increase the inlet temperature by 3 degrees, the net result would be the outlet temperature will increase by 6 degrees. Okay? So you can see that if you go back and redefine this transfer function, G is equal to 6 divided by 5 times S plus 1. And then plot the step of that. You see the y-axis going from 0 to 6 in terms of deviation variable. So the net effect of adding 42 kilowatts plus increasing the inlet temperature, and you need to understand the math behind it. Okay. So here I have both Q and T prime. Neither one is 0. So there are 2 excitations on the process. I'm increasing Q, at the same time I'm increasing the inlet temperature. But I'm increasing the inlet temperature by 3, and I'm increasing Q by 42 kilowatts. Okay? And when you simplify that, you will have this cancelling with this giving you 3, and 3 plus 3 gives you 6. Okay? So this is the net effect of having both of them. Any questions on that? Now the next question would be, if I combine it in such a way that I increase the inlet temperature by 3, but I decrease the heating rate by 42 kilowatts, what would happen? That is your control. Okay? So if your goal is to maintain the outlet temperature at the same value, if you know a priori that the inlet stream is going to increase by 3 degrees, we can figure out how much of heat I have to decrease so that I decrease the heating rate by that amount so the effect cancels out. So what happens here is it's the same combination of transfer function, but it is now minus 42 divided by 14. That gives you minus 3. Here you have plus 3. So add them up, it is 0. Okay? So there is no change. And this is what manual control is. You put an operator manning all the time the control valve, and if he knows a priori that the new stream is coming at a higher temperature, he can program it. Or he can be this part of the feedback loop. If he has a reading in the outlet temperature, he reads it before it's going up, so he needs to go back and bring it down. The visual kind of a control. Okay? So you get an idea of how the dynamical response is used to know what control action you have to take. Okay? Any questions? I'm not going to do this in MATLAB because you got the idea. Yeah. So basically what it says is one can develop a table, okay, for an operator who doesn't want to know these equations, doesn't want to solve. It should not laugh at this. This is how the operators are operating at one time. They will have charts, okay. So this is the temperature, this is the setting on the heating rate. Build a table, operating chart, or a graph, and he just looks at that and then just sets a number. Okay. That's a very good question. Right. The question that you are raising is a very good one, because what he's saying is, why detect the effect of the input change on the output? Wait for that, because it's going to take, and then create a reaction. Why not look forward? This is called feedback control, and that is called feed-forward control. And it is an algorithm that is used. But what you need to know for feed-forward control is you need to have a knowledge of the process. If you don't have the knowledge of the process, feedback control will still work. Because it will say, I'm just measuring it, I need to know how to change it. Okay? So having a process knowledge, meaning the transfer function for the process, helps in doing the feedback control. And we will see later on that we have seen one way of building this knowledge from first principles, how to develop the transfer function for a process. Another way, when I talked about this control station, you just make a change. You don't. The process is so complicated, you cannot build models. Okay? So you make a change in the inlet and observe the outlet change, and then fit a first-order process with a time delay. So you get these two constants experimentally. Then use that in your feedback control. It would work. But feed-forward requires very precise knowledge about the process, that you can know a priori and predict and then take a compensating action. That is an algorithm that is used, but it requires a very good knowledge of the process itself. That's a very good thing. Right. There are problems later on. We are going to see about stability issues. Okay, we already talked about an idea of what stability is, but control systems, when you're tuning, you can tune them in such a way that the control action that you take is overly compensating for what is happening. If you get into that loop, the feedback control system will be unstable. Okay? Feed-forward control system becomes even more unstable, particularly if your process knowledge is not true. Because you're anticipating some change and making an action, but it's not the wrong action, the process goes uncontrollable, unstable. Okay? So the stability issues will tell us why feedback PID controller is most commonly used and most robust. There are other control strategies, one they call model predictive control. There are many others in an advanced course. There is, of course, I think, following this. Some of you may do that as an elective. And you will see those techniques in there. There is something called the cascade control. There are many, many variations on this. But this is the manual control on how to do that. Okay. Now we are going to focus on the measuring element, okay, the thermocouple. So here is a problem. It says the temperature sensing element for the tank is a thermocouple. The manufacturer's specification states that the thermocouple has a response time of 45 seconds. Okay. And the manufacturer has to tell you what he means by the response time. And that definition of a response time is the thermocouple will reach 90% of the step change. If you put a step change on the thermocouple alone, leaving everything else out, it will reach 90% of the step change, the steady state value, in 45 seconds. That is what they define as a response time. So assuming that the thermocouple behaves as a first order system, find the time constant for the measuring element, plot the actual and measured response for a step change of 10 degrees in the inlet temperature. Okay, no change in Q. This we'll do in simulating. Okay, so the first question is find the time constant for measuring element. This problem is called the identification problem. Okay, so you have some information on the response. You use that to figure out the time constant, because otherwise the time constant is not knowable from the process. The process is either complicated or a first order process is a good model for that. In this case, first order process is a good model, but I don't want to measure the capacity, the mass, etc. of the thermocouple. I don't have information on that. A simple test will tell me what is the response time. Okay? Any questions? You understand the problem? This is from my last year's lecture, so lecture 22 should change it to 19. I'm going a bit faster. Okay? So the transfer function for the measuring element is given by 1 over tau m. Tau m is the time constant for the measuring element, s plus 1, because you are told that it is a first order process. So you know that this is the transfer function. So T prime is the change in the process temperature, and measuring element is going to sense that. So the block here is, let me just keep the same structure. So T prime is the one that comes from the process. Okay. So this is the transfer function 1 over tau m s plus 1, and what comes out is Tm. So it is relating what is being measured in the tank versus what the signal is that is coming out of the thermocouple. Now, as I said in the last class, if tau m is 0, there is no delay. Okay? As soon as the temperature changes in T prime, you sense it in Tm prime. But it is not true. So in this case, we need to find out how big this one is. What is its value from the given data? And what is the data? The data is it reaches 90% in 45 seconds. So how do you do that? How do you get tau m? Open loop step test, right? So that simply means we need to find, you know, the relationship for the open loop for a step change, unit step change. If I put a unit step change, this is the response. Okay? In the Laplace domain. So I can now get that in the time domain. Okay? So I'm going to define Tm as tau m. Okay? So that is the same in MATLAB. Okay? So I'm defining the symbols y, s, and Tm. And g in a transfer function is 1 divided by Tm s plus 1 divided by s. So I'm putting a unit step change. And I do the inverse Laplace transform on g, and I get the answer. Okay? The answer has Tm in it, symbolically. I don't know what Tm is at this stage. But so that simply means it is 1 minus e to the power minus t over tau m. What am I given in this case? I'm given that this is you have to figure out from the problem statement. Okay? The problem statement says that in 45 seconds it goes to 90%. So what would Tm prime be? 0.9, 90%, 0.9. Okay? If I put 1 degree Celsius change, step change, it is going to go up to 0.9 when T is 45 seconds. So in that equation, that is the open loop equation relating the output to the input, you know T and you know the Tm prime. So you have to solve for what this number is. This is again something that's very similar to what you did in your first midterm exam. Okay? So rearrange that and solve for Tm. In MATLAB, the way that you would do that is This is the equation after substituting the numbers, and you want to solve for Tm. So the solve and put that expression in quotation. So symbolically, it solves for Tm, the symbol Tm. How many other ways you know how to solve that? Yeah. What roots do? Roots won't do here because it's not a polynomial. Roots always works on a polynomial expression, finds all the roots of a polynomial equation. So if it were something like Tm cubed plus 5Tm squared, etc., equal to 0, then you can use the roots. But you will use the coefficients from that as input to the roots. But there is f solve. F solve, you need to write this as a function and input the function. Okay? Whereas solve simply takes the expression and solves it symbolically. Sorry, I think we're running out of time. So that gives you Tm. This is the problem with the symbolic output. It gives you a long number of digits, but truncated to 19.5 seconds or 0.33 minutes. That is the time constant. Okay? So in the next class, we will follow up the simulating part. I think it does, yeah. Solve can take any complicated expression with lots of symbols. You identify one symbol that you want to solve for. It simply moves everything else to the other side and rearranges them. Three variables. I think it's possible to do. I think so. Yeah.